Hi, good evening. Today we will tackle about the Newton-Rapson method. See here is the Python code. It uses tkinter to create a graphical user interface or what we call GUI. Newton-Rapson method, which helps find the root of a mathematical function. The user inputs a function and initial guess, a tolerable error, and a maximum number of iterations. The code can iteratively apply the Newton-Raphson formula to compute the root, displaying the results of each iteration in the GUI, and stops when the error threshold is met or the maximum iterations are needed. This code implements the Newton-Raphson base to find the root of a mathematical function. Also, this given code iteratively updates the guess based on the formula x sub 1 equals x sub 0 minus f of x sub 0 over f prime of x sub 0 until the error is small enough or the maximum iterations are reached. Now, for the Newton-Raphson method, it is useful in our real life. It can be used for solving complex questions where analytical solutions are difficult to obtain. It is widely used in fields such as engineering, physics, and finance to find roots of nonlinear equations, like in optimization problems, circuit analysis, or calculating interest rates. Now, for us as an engineering student, it can be used in real life by this kind of digital signal processing. In Newton-Raphson method, it is used to find the roots of nonlinear equations for designing filters, such as determining the cutoff frequencies of low-pass filters. This iterative method helps engineers efficiently and accurately solve for poles and zeros, optimizing filter performance in real-time applications like audio and communication system. Now, here, with the given code that uses tkinter, we can now run it. And wait for a while. Same here is the GUI. Now, with the given problem for the digital signal processing, we can enter a function of x sub 3 minus 2x minus 5. For the initial value, we can have it as 2. For the tolerable error, we can use 1e minus 6. And for the maximum iteration, we can use 20. Now we can click here. There's a syntax. I think we can make it with this one. Okay, so if you could not pass because of main reasons. Wait for a while. I'm just figuring it out. Can have it by x. So x raised to 2 minus x minus 1. Sorry. With IE minus 6. And there is it. Sorry for the minor error. Now, for the function of f of x, we have x raised to 2 minus x minus 1. The initial value is 2. The tolerable error is IE minus 6. And the maximum step of iteration is 20. Now you can see here is the answer for the new Rapson method implementation. It stopped when it met the stopping criteria. And the required root for this is 1.6180 And that's all for Newton-Raphson method. Thank you.
So, good evening. My name is Ramiro, and today I am going to present my project on the Gauss-Seidel method for solving system of linear equation, which I have implemented using a graphical user interface, or GUI in Python. First, what is the Gauss-Seidel method? The Gauss-Seidel method is an iterative technique used to find solutions to linear equations of the form of ax equals b. It is particularly useful for large systems where direct methods may be computationally expensive. The method updates the solution iteratively using the most recent values as soon as they are available, which can lead to faster convergence. So this project has three goals. The first one is to implement the Gauss-Seidel method in Python. The second one is to create a user-friendly GUI that allows user to input their own matrices and vectors. Then the third one is to display the results including the solutions and the iterations in a clear and organized manner. So in this program, I use the takinter library to create the GUI, which is included with Python and provides a simple way to build desktop applications. The user can input the number of rows and columns for the matrix, and then enter the elements of the matrix and the vectors through dialog boxes. The program computes the solution using the Gauss-Seidel method and displays the results in a scrolled text area, making it easy to read. So, let me show you how this program works. So, after you run this program, this code, this will be the GUI. So here, let's try the value. The number of rows, we'll try the 3 by 3 matrix. Then solve. So after you click solve, this window will pop up. So you will enter the values of your matrix. So the first one will be 5, -2, then 3. Okay. -3, 2, -7. After you insert the values of that, then here you will enter the vectors of the matrix. After completing or inputting the matrix and the vectors of your matrix, um, here you will see the final result. So here you can see the solution the of the given functions or equations. So here you will see the iterations. The iteration will stop if if the present value is the same as the previous value. So that's it.
Hello, I am Emil Kit Ramos and I'm about to present my project Gauss-Jacobi method using the Python code for solving linear equations, which I have implemented using GUI or graphical user interface. So to start the topic, I'm going to define first the Gauss-Jacobi method. The Gauss-Jacobi method is a step-by-step approach in solving systems of linear equations, especially when dealing with large problems that are too complex for direct methods like Gaussian elimination. Instead of solving everything all at once, it works by breaking the system down into smaller, simple calculations. Each variable in the system is updated one at a time using an initial guess and then improving it gradually with each iteration. This process continues until the results are close enough to the actual solution. The method works best when the equations are set up in a certain way, especially when the diagonal elements of the matrix, the main numbers in each equation, are larger than the sum of the other numbers in their row. While it's not the fastest compared to other methods like the Gauss-Seidel method. Its simplicity and ability to handle multiple updates at the same time makes it appealing in some situations. It's especially useful when ease of use adaptability are more important than speed. So for that, I'm going to show you and I'm going to run the code. Then the GUI will pop up. So the for example, I'm going to create or type 3 by 3, three columns, 3 rows and 3 columns. Then this one will pop up the elements. So I'm going to type for the is column 1 is 4.5. Then column 1, row 2 is 1.0. Then 0.8. And then for the column 2, row 1 is 1.2. Then 0.8. Then 1 1.0. And then 0.9, 1.1, 4.3. Then the next one is the vector B. For the element 1, going to type 6.8. Element 2 is 7.4. Then for the last element 3, I'm going to type 5.9. And press OK. Then after that, uh, it will shows here that the final result was the solution by Gauss-Jacobi method. Uh, so here you can see the solution of the given functions. or equations. Yeah. And then here you will see the iterations. Yeah. Then the iterations will stop if the present and the previous value is the same. Yes. If the previous and the present and the previous value is the same. So that's it for the Gauss-Jacobi method. Thank you.
Hello, I'm Raven Palaypayon, and I'm about to present our project Regula Falsi using Python code solving linear equation which I have implemented using GUI or graphical user interface. And first, I am going to explain what is regular falsi or regula falsi. Regula falsi is also known as the false position method. It is a numerical technique used to find the root of a nonlinear equation of the form of f of x. This method is based on the concept of bucketing, where two initial guesses, x0 and x1, are chosen such that the function values at these points have opposite signs indicating that a root lies between them. In this code, we will discuss regular falsi method in detail, including how to use it and as well as on giving an example. Now I am going to run the code for you to see how this calculator for regular falsi works. Okay, so we're going to put here for the function in terms of x is x x cubed minus x minus 2 here, and for the interval is 1 and 2. Tolerance is 0.001. Okay, so on this, we will see that the tolerance is 0.001, ensures that the solution is accurate up to the 3 decimal places, which you could see here is the root 1.5213. And on this project, it demonstrates the power of combining numerical methods with intuitive user interfaces, helping both students and professionals solve complex problems effectively. And that would be all. Thank you.